Henrik, and then we have Sopit. No, then we have Tim and then Sopit. Thank you.
Well, thank you for hosting me tonight. I'm Kenrick Nelson. I work at Raytheon on supporting the Missile Defense Agency and at Boston University as a research professor. This is a talk I gave last week at the International Conference on Complex Systems, also here in Cambridge. But I thought it would also be of interest to this group. And the heart of what I'm going to talk about is that the machine learning techniques are very powerful. And I'm actually not going to talk a lot about the power of those techniques. I'm going to talk a little bit about some ways in which they're brittle and try to give an explanation for why that might be and what some ways that you could do some new measurements on your own techniques and find out if your own techniques are susceptible to these issues. And then I'm going to motivate some ways that you might resolve them, but I don't provide a solution here. But but the techniques also kind of motivate some potential solutions. And I'm going to start with one of the most one of the more terrific results in machine learning from a group here at MIT. Josh Tenenbaum's group a few years ago presented a result in which they achieved better than human recognition on a variety of different problems. One of which was to recognize these scripts that are kind of convoluted and complicated. And the way they approached the problem was to use probabilistic programming to learn segments of the problem and be able to reconfigure those segments into solutions of patterns. And they achieved 96.7% classification, which was better than the human results, which is shown here in purple, and much, much better than other established techniques in machine learning. The other thing that was nice about their publication is they also reported what's called the log scoring rule. And this is a way of measuring the accuracy of the probabilities that are associated with what you predicted to be the truth. So these numbers here below each figure, minus 550, minus 593, are the log scoring rule. The problem is those numbers are very abstract. This has to do with information theory. And once you take the log of the probability, nobody really understands what that number means. So what I've been doing in my own work is I've been taking that log scoring rule and translating it back to a probability. And I do that over here on the right. You can translate it back by taking the inverse of the log, which is the exponential. And these numbers correspond to probabilities that are exponentially near zero. These are extraordinarily small probabilities. So the probabilities associated with the truth here is 4.8 times 10 to the minus 200. And one of them here is minus 780. So the question is, how can you have such extraordinary results in classification while assigning probabilities to the truth that are exponentially near zero? So that's what motivates this talk, and I'm going to talk a little bit about how that happens. So here's a much, much simpler model, sort of moving away from machine learning, but going to just some very basic characteristics of statistics that machine learning is based on. Here I have just two classes, red and blue, and the solid curves represent the true distribution that I'm going to draw samples from. And the dashed and lighter colors represent the model that I'm going to use. Now, this distribution turns out to be not exactly a Gaussian. They look Gaussian, but the solid curves actually have a long decaying tail here. And the model I'm using is a Gaussian, which is a very typical model. And the decision boundary is still at zero. So even though the model is off, I haven't changed my classification performance at all. Right? And so if all I measure is my ability to classify correctly, I'll never detect this error. If you see on the right here, the right curve here is the posterior probabilities that are being reported. If you had a perfect model, they would perfectly match these solid curves here. But our model is Gaussian, and what happens in the exponential family generally and in the Gaussian is that as you get away from your decision boundary, your certainty about a particular class saturates to 1 and 0. And that it's out in the tails here where you get these probability estimates of being 10 to the minus 200, for instance, as we saw in the other example. And the problem is the metrics we use to test the performance of machine learning techniques aren't at all sensitive to this mismatch in the models. So I'm going to now talk about some ways that you can actually start to measure this. And the way I do it is I do two things. One, I take all the kind of complications of information theory and I take the results of information theory and I turn it back into a probability that represents the average of the set of probabilities I started with. But the distinction here is that when I take the average of a set of probabilities, I need to take the geometric mean of those probabilities rather than the arithmetic mean. And the reason is that the probabilities reside on a multiplicative space. In fact, Shannon's insight, for those of you who know a little bit about information theory, was that you could measure averages of probabilities by first taking the logarithmic average. By taking the logarithmic, if I take the log of the probability, now those are on an arithmetic scale, and I can sum them or take averages and other kinds of statistics. But you can't do it on the probabilities directly. There's a second piece to this that I'm only going to do sort of cursorily tonight. But it turns out there's been a lot of work to kind of generalize information theory, and you can actually form kind of a spectrum of metrics. If you translate those back to probabilities, it turns out the metric you get is the generalized mean. Which is a whole family of means, including the arithmetic mean, which I'm now going to use to measure how decisive the probabilities are. And then if I go to negative means, I'll actually invert the probabilities, and that will be very sensitive to what's happening in the tails. And that's what I'm going to call a robust metric. So on this simple example here, the classification performance was 90% and didn't change. And my decisiveness metric, which is the arithmetic mean, is similar to that, 85%. And almost always you'll find that the arithmetic mean of the probabilities is very similar to your classification performance. But you can see here now with this new metric, if I measure the accuracy of the probabilities using the geometric mean, it drops from 77% down to 40%. And so that's where you can have a really terrific machine learning algorithm that has 80 to 90% classification performance and still have very bad models that have really no ability to accurately forecast the uncertainty in your classification. And then this robustness metric is even more sensitive because essentially what it's doing is actually filtering out the areas near the decision boundary and only evaluating how good the tails are. And I go from 62% down to this exponential minus 15. So what's the consequences? The first thing is that machine learning techniques are very powerful. We're using them around the world for solving really difficult problems. And they're working without people even being aware of this issue. So part of the point is that if you're making decisions over a small number of states, then the accuracy of the probabilities assigned to those states isn't actually that important. And the only thing that your decisions is sensitive to is that you got the order of the probabilities correct. On the other hand, there are other kinds of problems where you really are trying to kind of allocate resources across the states rather than just picking one of them. The classic example is a trader who is making bets and wants to know how to distribute those bets in order to optimize their profit and return. But there's all kinds of other examples where you're trying to allocate limited resources across a set of states, and now how much you allocate matters. The other thing, and it's not to suggest that there's a proof here, but there's also a lot of evidence that the current techniques in machine learning are very brittle. And it's my claim that the brittleness comes from the fact that we're not paying attention to how to manage the uncertainty in these algorithms. And then finally, in any kind of technique where you're going to report probabilities and then try to fuse that information, and particularly if you're going to try to use Bayesian reasoning to fuse those probabilities, then the accuracy of the probability matters a lot. And these errors are going to multiply as you try to integrate more and more information using techniques like a Bayesian network. So again, not really I'm not going to go over the equations, but I just want to kind of re-emphasize that the whole body of techniques that I'm using starts with the assumption that you need to care about heavy tail distributions, like the student T distribution, which I showed at the beginning, and which in my own work I refer to as a coupled Gaussian because I'm particularly interested in nonlinear systems. From there, you can derive a generalization of information theory that gives you an appropriate way to combine information in these kinds of distributions. And that then leads to a technique for fusing information in a more robust way. I'm not going to go into the details of that, but this is ongoing research about how to design new machine learning techniques that would use these more robust fusion methods. I'm going to give one more kind of motivating example, and then I can take some questions. But actually, maybe I'll pause and just, before I go into the next example, are there some questions right now? Everyone okay with me going on? Go ahead.
Why do you practice? You said that with distributions like heavy tail,
yeah,
you need more general a framework of information theory.
Yes.
But doesn't just the classic Shannon information theory work no matter the distribution? So to generalize it.
Okay, it's a great question. I hope in my backups I can provide an explanation. Yeah. So this is why you need to generalize it. And I will say this is an open, controversial question. So some people will say that you shouldn't generalize it. Here's, again, by translating it back to probabilities, I can show exactly why this is really valuable. A lot of people have heard of the concept of entropy. You may even know the mathematical equation for entropy. But if I give you a Gaussian distribution, what part of the density represents the entropy? And I'll just give that as a thought question. I'm not asking you, but as a rhetorical text, if I measure the entropy of a Gaussian distribution, and then I translate that information theoretic result back to a probability, what probability do I get? And how is it reflected on the distribution? So over the last couple of years since I discovered the answer to this, I have asked the world experts in statistical mechanics, in mathematical statistics, and they don't know the answer to this very fundamental question. It turns out that entropy of a Gaussian is the probability at the mean plus the standard deviation. So we all understand what a Gaussian is, and we have a mean in the center here, And we know that the standard deviation is a measure of the amount of uncertainty. But how many people realize that the density at that point is the entropy of the distribution? And this is my important point, is that I think when you translate it back to a probability, you get a lot more intuition. And so the entropy is measuring the average density of the distribution. Now, as I go to heavy-tailed distributions, and I have several of them in this family here, if I do this same thing with just Shannon's entropy, then the density that I choose is going to get smaller and smaller and eventually go to 0 as the variance and standard deviation of these distributions goes to infinity, right? However, the student T still has a scale here, and you can use that same symbol here. And it turns out these generalized information metrics give the exact same point. The mean plus the scale is the probability that these generalized metrics give you for that density. So what it's doing is it's separating out the two things that are creating uncertainty. One part of the uncertainty is the fact that I have a slow tail that's causing a lot of uncertainty. But by making that part, separating that out within the metric, I can then also determine sort of the uncertainty that's due to the scale or width of the distribution. So I appreciate that question and hope that helped explain. And there are other speakers tonight, so let me skip a little bit, and I can talk more later. Let me skip that second example, and just let's see. Let me show you. I'll show you this. It kind of is motivated by this one. I'll show this example. So I've been working on some techniques to apply these methods to make systems more robust. And I call the concept coupled fusion. The tree here you might recognize as it could be either a Markov process, or if it was directed, it could be a Bayesian network. And typically you're assuming kind of independence between the variables. And the structure of the tree is kind of defining the linear correlations between the variables. What I do instead here is I'm actually not applying any linear correlation at all in the model, and instead I'm coupling all the variables together with this non-linear function. And what I've been able to show is that you can achieve as good accuracy with just one parameter as you would require with tens of thousands of linear correlation parameters. And in this example, the way I showed it is that the problem is to classify handwritten numerals, and this is on the machine learning repository. And you're given a variety of features. And let me just take one example as the pixels. There's 240 pixels. And if I can make a multivariate Gaussian with that, if I assume all the features are independent, then I have what's effectively is a naive Bayes solution. And I can classify, but down here in this region, I'm showing that the accuracy of that model is very poor. On the other hand, I can model all of the correlations, and I can get very high accuracy, up to 60 or 70% in the probabilities. But I need tens of thousands of parameters to do that. But with this coupled Bayesian method, I just need one nonlinear parameter for that fusion technique, and I get as good or even better accuracy. I think for tonight, I'll skip this chart. It gets a little complicated. And I'll just end by saying that there have been some publications about applying these techniques in more complicated problems in machine learning. And this was two examples that, if there's time afterwards, we could talk more about. And with that, I'll end with just this one thing. If you only take one thing away, don't just measure your classification performance. Assign probabilities to your classes, And for the true class, take the geometric mean of all those probabilities. And that will tell you what the accuracy of the probabilities are. So with that, we can either transition to the next speaker, or if there's time for some questions, we can do that. Anyone have another question? Yeah, go ahead.
So you're aggregating the variables,
Yeah.
and then you're cutting off the tails. So I'm not a mathematician. Just
Yeah.
aggregating the variables and then making the model more robust by combining both the distribution and the standard deviation into one number. Is that incorrect? That's totally incorrect.
Well, let me try to rephrase it and get to the point I think you're trying to make, is that the current techniques, although we may not ever think about them, they're almost all of them are derived from properties of the exponential family, and particularly the Gaussian. So just as an example, when we measure the mean and the standard deviation, you can certainly take that measurement on all kinds of distributions, but it's really only meaningful in characterizing the uncertainty within the exponential family, and particularly the Gaussian. And when the actual source of information that you're trying to model actually has these slower tails, the standard deviation, for instance, can very easily go to infinity. And so whatever measurement you get is actually quite meaningless. So we need to kind of move away from this reliance on particularly the standard deviation as always being a reliable measurement of uncertainty. And then from there, it also motivates this idea that while Shannon information theory is a very, very powerful technique, it has some gaps too. There are things, you're always aggregating things, right? So you're always taking a set of numbers and reducing it to one. So you're taking an average, and that average has particular properties that don't really match up well with heavy tail distributions. Is that helpful?
Yeah, so the models, are we drinking our own Kool-Aid in some of the models that we're assuming all of these mystery variables, and in fact, we're just tricking ourselves?
I think so, yes. And particularly where we're getting tricked is that almost always the performance of these tools is measured by measuring how good you can classify. And that is the first thing that may be what you're trying to accomplish. But in doing so, just because you have good classification doesn't mean you model the uncertainty in that classification well. And in particular, if you care about being accurate about the uncertainty, it's very important that you use models and techniques that allow for slower decay in the tails than you would ever actually see from the source of information.
What's the relationship between this and deep learning?
There may be other talks on deep learning. The deep learning techniques, use layers and layers of aggregation. In fact, the original technique, the examples, I haven't done an example myself using the deep learning techniques, but these examples here with the references and this particular example are using things like deep learning. Their technique here was a combination of deep learning and probabilistic programming. And it was also kind of a comparison of probabilistic programming with deep learning techniques. Again, I can't say that I've proven this, but because of the way deep learning the way the feedback is often, you have to measure some error. right, in order to propagate that back and learn your network. Oftentimes, the error that's propagated back is the classification error. So for sure, that's not going to be sensitive to modeling the uncertainty. Sometimes there are lots of efforts where they'll measure what's called the Kolbeck-Leibler divergence. And that is much better because it is measuring and it is sensitive to the accuracy of the probabilities. But part of my point is that itself may not get to all of it because, again, that is derived from properties of the exponential family. And the heavy tail distributions will be a little bit different. So, all right. Well, thank you very much. Appreciate it.
Testing check. Hi guys, my name's Tim Moody. I'm going to be talking kind of more high level about how businesses online are using machine learning. Just a little background. I work in testing and optimization, so I help online retailers who are operating at scale to deploy new features, deploy new technologies, test those technologies, test the impact on their particular KPIs, and then measure and report on those findings. Again, this is much more high level. A number of different companies using these techniques and a number of different approaches. But hopefully after this talk, you guys can have a kind of good sense for like how are companies applying these techniques to actually generate some money and an ROI in their business. So the biggest thing that I've seen with companies is just either applying these techniques to generate automation in their business or optimization. So I deal primarily with optimization, which is taking some sort of process that they're already doing and making it more efficient, more effective, faster, reducing process time, and all that equates to resources and money and that sort of thing, or development time, which work hours, those sort of things. But automation is definitely something to think about. You know, the advent of ATMs obviously had an impact on the people who were providing that job prior to this service. So ATM is automated teller machine. So, you know, people were presumably performing that service. The technology came to kind of a point where through the hardware, software, and then some pretty sophisticated software, they could perform all those tasks with, you know, just a machine. And you know, I think, you know, we're seeing a lot of this more and more, but, you know, we kind of had the first wave of automation with this sort of thing, kiosks, that sort of thing. And I think one of the bottlenecks was just, there were still so many tasks that only people could do, you know, software couldn't do. If you think about OCR, NLU, that sort of thing, you know, we still, it had been done, but it wasn't as accessible as it is now. And I think we're past that point now. So I'm just thinking that there's going to be a second wave of automation. It's definitely something to think about. Probably not for us in the particular space that we work in, but for friends, family, that sort of thing. You know, we're just seeing more and more. You know, this is the McDonald's that's next to my office, and this is what they're up to. You know, using technology software. You know, it's the same exact idea. Going on again, you know, flights, toll services, all that stuff. Just automating these services using the newer technologies. And if you look at that trajectory of automation, you know, I'm not going to have a job in a year. Just kidding. But we can see like that's what's going on. So you know, there's just more and more automation. It's eating away at kind of the processes and a lot of jobs. And really, all of logistics, Amazon, Whole Foods, that's going to turn into just a more automated, streamlined experience. So that's automation. Again, that's not my specialty. That's not what I work in. I work in optimization with businesses using software to sell things. So all the businesses I work with fit this profile, which is they have some sort of application. It's usually a web application along with native applications, Android, iOS. Sometimes they have kiosks. Sometimes they're doing things with TVs and other devices. But the application has some sort of funnel. So user interfaces with data, views products, something along those lines. And then they convert. And usually that means transacting monetarily, but that also can mean generating leads. For some of our financial institutions, it's just signing up, creating an account. So there's a number of different metrics they could use as their conversion metric, but typically it's just orders, revenue, that sort of thing. So we're just trying to make the user experience easier by requiring them to do less. So the most straightforward example is just all our businesses, all the clients we work with need to know if a user is a bot or an actual user. And this is kind of the way they were doing it before, which is they're issuing some sort of challenge, and the user had to select the element that fits the tile that fits some sort of category. It's kind of silly if you think about it. Someone basically realized that actually a user just visiting a website or opening an app and then selecting a checkbox is actually a lot of data, because they're generating data about the amount of time they spent on the site, the coordinates of their mouse, and other things like that. And from that data, you can actually classify if a user is a bot or an actual user accurately. And I think the next permutation of this will just be, it'll be all under a user will just be, you'll be able to detect if a user is a bot just by how they're interacting with the site, and it won't have to, the user won't have to explicitly provide any information. So that's a straightforward example. So we work with a lot of retailers. Recommendation engines is a big space. Most of the sites that you go to, unless it's like Amazon or one of the really big sites, they're probably not serving up these recommendations in-house. It's usually a third party. So Reflection is some guys from Google. Certona is a popular company. Rich Relevance, they all just do recommendation engines. That's all they do, is that widget. And the company that can provide the assortment of products that is most lucrative for their client will win. So one thing I'll say is, every time we're testing new technologies, we're not just naively throwing it on the page and kind of just like looking at the impact on revenue. We're actually deploying it as an A/B test. Or in a case like this is a bake-off style ABCD test, and we'll do head-to-head vendor testing. And after a month or a period of time, we can definitively say how each vendor performs, and then we can make that decision if we want to deploy that vendor or go into a contract with them. Malware Blocking. This is a company based out of Tel Aviv and Boston, Namogu. Essentially, they've identified that there's a large percentage of compromised machines. They have malware of some kind, and the malware has the capability of they call it journey hijacking, but essentially it can generate ads on a site. It can generate like competitor products can be shown on a client's website, and basically ultimately distract the user or keep them from converting. And so what they do is they monitor the network traffic on a particular machine, and they're able to tell. They have a classifier that can tell if that machine's compromised. If it is, it can do whitelisting or blacklisting of any traffic that seems nefarious and that sort of thing, and it can block those ads, and then that revenue can be recouped for the client essentially. Again, we would deploy this as an A/B test. So if you go to Namogu's website, they're going to state, we increased conversions by 10% or something, or they'll have some number, and we'll actually put that to the test and say, great, let's do a 90-day proof of concept, and we can see what the actual incremental revenue increase is on their particular site. I guess one thing I'd say about all these tools really is they're all able to generate, they're all able to take a user's data that the user's generating and send that off to some third party to be crunched or turned into a model and then deployed to, and then used to deploy some logic to make a change for a user. But essentially it's just, we just import the dependency for the particular vendor, and then they can listen in on particular events, or in this case it's network traffic, and they can compile that data into some JSON object and send that back to the Nimogu servers, and the data scientists can create a model from that. And then when that model is matured, they can deploy that to actually they can use that to actually deploy this feature, which is to block that nefarious traffic and enhance the end user's experience. Another thing we do is just like more sophisticated marketing. You guys have probably all seen these pop-ups that come up and they offer 10% discounts or whatever. Do something, provide your email, and there's some incentive. And then the only way to dismiss it is by saying that you like to set money on fire, which I find particularly annoying, or that you don't like to save money or something. Anyways, they're kind of annoying. They are just a way to barrage every user. One thing to note is they work. If you deploy this on a website, it will increase conversions. It'll increase revenue because you're offering some sort of discount. The next question would be, is it a good idea in regards to kind of like branding or how much you're annoying users, or some people might just see a pop-up and just stop navigating the site, close out of the browser, that sort of thing. And then the other thing is a 10% discount has a revenue impact. So sure, it's going to increase conversions, but on the back end, what's that 10% discount that we just gave to everyone? So it's just kind of a brute force way to generate some incremental revenue in the short term. So this company I really like. What they do is they say, first, you import their dependency into your site, and they just spend a couple weeks just listening. So when I go to, for instance, Amazon.com, I generate a ton of data. I visit certain pages, I visit certain product SKUs, I interact with the images with those product SKUs, I add items to basket, I remove items from my cart, I go to my cart, I maybe log in, I don't log in. There's just all this data that is able to characterize my interaction on that website. And so this company listens for about 2 weeks, and then they come up with a model that essentially it's able to detect your propensity to actually converting on a site. So if you look at this graph here, to the left, that would be a user who this model is identified as 100% chance or a very high probability that they're going to convert. We're looking at their user behavior, and we can just see their intent is very high. And then to the lower right, you can see this user is not going to convert based on the way they're interacting with the site. And so what this company says is, instead of just barraging everyone with these pop-ups, we don't need to send pop-ups to people who we know are going to convert already. And we also don't need to be giving them discounts. And we also don't need to be sending pop-ups to people who are not going to convert. So that green square is really the only users that we care about. And you could say those are the users who are on the fence in terms of converting that could actually maybe benefit from a nudge. And that's exactly what they do. So once this model's complete, instead of barraging everyone with users, they just target that group of users. And they just do things like marketing 101 tactics, scarcity of inventory. Like this item is selling fast, or this item is in low inventory, or social proof, X number of people purchased this in the last several hours, that sort of thing. So no revenue impact, there's no discount. But they can just they can do some kind of incentivized messaging, and they can really only show it to the users who are going to benefit from that incentivized messaging. And so we would deploy this as, again, an A/B test, or if we wanted to go head-to-head with that other vendor, ABC test. And then we would just report on it like this. We'd say there's a control group, there's the Granify tag or the Granify model. These are the number of users, these are the number of orders. There was a lift in orders of 3.54%. Average order value didn't really go up much, but that's okay, as long as the volume of orders is going up. and then we could report on revenue per visit and that sort of thing. And then we can say over the 1 month period there was an incremental revenue lift, and we can report on that. And if they're satisfied with that, we can deploy that into production. But yeah, so the actual model is something that's maintained, and it's built by the Granify systems. We're just essentially sending data and interfacing with that system. But they give us that script. We just say import Granify, and then it just does everything. And they can even remotely change that code that's going to be imported. So very, very hands-off for the actual client, but we're able to kind of glean the expertise that they have. And they're doing this across retailers, across verticals, so they're able to become really clever with it, essentially. Discovery, so search is another big thing. A lot of these sites, this is Bed Bath & Beyond, they're not doing search in-house. They're relying on third parties to do that. They have tons of products, and sometimes they actually are pulling in products like Google sponsored products and that sort of thing. So there's usually some sort of third party under the hood there that's taking care of their site search, and they might do testing on that. These are some of the popular companies that we've used. And then there's just a bunch of other kind of like things that are coming up that companies are doing. Similar to recommendation engines. How do we organize products in a way that makes sense? If a person just purchased a dishwasher, like, do we need to show them more dishwashers, or should we show them something that makes sense, like an item that could be coupled with dishwashers, that sort of thing, and just ensemble curation, that sort of thing. So there's this company here on the left called Shoptelligence, and that's literally all they do. They look at your inventory, and then they try to come up with kind of ensembles of inventory that are most lucrative for you, and they test those different assortments. And then on the right, this is another company, Stylytics, just mixing and matching different products, and ultimately getting users to buy more products. So this is another company. This is a little bit over into AR, VR. Avametrics, really cool technology. So what they're trying to do is not get people to buy more. They're actually trying to reduce refund or returns. And the way they're trying to do that is by saying, how do we eliminate the need for dressing rooms? And they've created this really nifty technology so we did an implementation of their technology that's not using the native app, so it doesn't have that AR component, and I'll show you guys it after. But the premise is you put a model into a real space, and you select the body size and the body type of that model, and then you select the garment that you actually are interested in buying, and then you can select the different sizes of that garment, and you can see how that garment actually falls on the model. And this company actually scans every single garment. So it's I don't know, it's pretty cool. It's very much in its infancy, but that's the premise of Avametrics. Let's see here. To go full screen, do I have to? Oops. Okay. I'm not sure. Oh, you know what? Perfect. Okay, so yeah, so we did an implementation of Avametrics. Let's see here. Yeah, I can show you guys this tool. So you come to the product that you're considering, and then should show the widget. No, it's still loading. Okay. I don't know why. Okay, so that's one of the things about A/B testing. I guess I'm in the control group potentially, but essentially, yeah, there would be a try me on widget. You click it, and it brings up that same exact thing that you saw in that video there. So I don't know how effective that's going to be, but it is an interesting concept. Okay, and then the other main thing is just NLP, NLU chatbots. We're just seeing a lot of this, probably pretty obvious. really revolutionizing how people interact with sites. This is American Eagle. They just rolled this out. Drift, really getting a lot of press right now. Vanguard just released a chatbot that actually hooks into their API and can do things like changing account names and that sort of thing, and you can just do it through kind of a conversational mode. And yeah, Vanguard is one of the clients that we work with. So yeah, the installation of these tools, one of the things I would just notice is super straightforward. So these companies like Bed Bath and Vanguard, like they for as far as marketing goes, they don't have machine learning experts, so we're deploying these third-party tools. It's really easy to do. It's just by inserting some scripts usually onto the page, and then that script is able to remotely call for new code that can be executed, and that code can gather data. It can make changes to the actual application itself. And the third party can do that all themselves. So these installations are usually super straightforward. So that's the Granify installation. This is the Avametrics installation. I just throw this on the page, and it's able to do everything that it needs to do. And then this is just the final project that I've been working on. Is just I don't just work with online retailers. Sometimes I work with other organizations, and when I do that, I use this tool that I built called MacGyver. But basically, this is a project that I'm working with actually the Indian government on. But it has to do with taking images, portrait images. So it has to do with identification verification. So you take these portrait images, and then you kind of measure along a bunch of different dimensions how it classifies. So they basically want to streamline their acceptance rejection program within their application, and they want to use machine learning to do that. So I did come up with this demo for them, and I'm on like the 5th iteration of this. But essentially, the way it works is on the platform that I built, you can upload your model, and then it's just your model is just exposed as an API that can be used by basically anyone. You have to have a key, and a lot of these models aren't free, but they're able to send over this data here. So this is just a reference to an image, and then we're able to respond in kind with those dimensions that I mentioned earlier. So they wanted to know if the image, if the person is wearing sunglasses. There was some concern about the face being too small. There's something about the resolution of the image. They care about the background color, whether the image is in color, whether there's actual face in the image, whether the user is faced directly towards the camera or if they're kind of slanted or that sort of thing, whether they're using reading glasses, whether it's full body, whether there's multiple faces, and then the background color, because if it's not close enough to white, they'll reject it. So it's similar to these other tools like Granify. Like they don't have the expertise, or for some reason haven't built this internally, and they're going to make a call to another platform. In this case, it's the MacGyver API, but it could be the Granify API, the Stylytics API, or Avametrics API. Their application will just send over that data, and then we'll take care of executing the model. In this case, it's just an image classifier that's pulled from Google, the Inception model, and then it's able to classify along these dimensions, and then we would just respond back, and then their application could perform the actual logic, which is accept or reject. So that is another project that I've been working on. And yeah, if anyone wants to get involved with deploying models and that sort of thing, the platform that I built can support really any programming language. We just use Docker containers. So the way it works is you put your program in a Docker container, and then you tell us the runtime you want to use, and we'll execute that program. And we don't really care what it does. So in this case, it would be Python. The program is just a Python script that pulls in TensorFlow and a bunch of other dependencies, and downloads the asset, runs the model against the asset, and then just prints out a JSON response. So yeah, I'm open to talk with anyone if anyone's interested in using that. So that's all I got. Thanks.
Any questions?
Cool. Thank you.
Thank you, Suprit.